Okay. So project number 2, I've moved the due date to Friday at noon. Test number 1 will be over chapter 2 material, and I'm 95% confident that test number 1 will be Tuesday, October 2nd. And obviously, we need to get through chapter 2 material first. Ideally, it would be nice for you to have some kind of feedback from me regarding your project. So perhaps what I will end up doing is, after everyone turns their project in by noon on Friday, I'll post an answer key to the web so that you at least have some general idea of what you did and did not do correct on the project. Are there any questions before we go on here? Yeah.
So I was a little bit confused as to the interpretation of big L. I understand mathematically how to show it and what's going on, but when you see it, how should you be thinking about it?
Okay. Easy way. I think I've always found little o easier to work with because it goes to 0. At the very end of my rates of convergence document, towards the end, I talk about the relationship between big O and little O. And that is, you just take, let's say, n to a little bit higher power. Let's say you have big O 1 over n. That's, you can think of that instead as little o 1 over n squared. You just need a little bit higher power there, and you get convergence to 0. I think it's just more of a matter of preference between if someone uses big O versus little O. But we need to talk about both, since some people use one, some people use the other. Any other questions? Okay. We will talk about project number 2 maybe about halfway through the class today, so it will be good to have that handy as well. Okay. So we're going to talk about something called an influence function. Influence functions are sometimes introduced in the asymptotics course, and they are always introduced in a PhD level non-parametrics course, which we do not have here. And what influence functions are used for is to measure the robustness of a statistic. So for example, in your very first stat course, you learned about how the median is a more robust measure of centrality than the mean is, because the median is less affected by outliers. And essentially what the influence function does, it measures this amount of robustness with an actual mathematical function. That's all. Now, the influence function is also used to obtain what's called the non-parametric delta method estimate of the variance. That's what we're really interested in this class. We're not interested in robustness, so don't worry about that. We are only interested in being able to calculate the influence function and then to apply it to get this non-parametric delta method estimate of the variance. That's it. So what I'm going to do today is give you a little bit of motivation for where this non-parametric delta method estimate of the variance comes from. And then we'll go into some examples that actually apply the corresponding formula to some problems. The reason why we want to get this non-parametric delta method variance, give you the big picture, is because remember when we talked about the studentized quantity and also the corresponding bootstrap version, let's say for the R3 sample. So the reason why we want to know about the non-parametric delta method estimate of the variance is because we need to get this part of this studentized quantity. We need to be able to calculate it rather easily. We've only taken a look at some examples. Well, I guess in class we took a look at some examples where it was fairly easy to derive. You know, like for example, when we're working with a sample mean. Well, you know what the variance is. You don't need any kind of distributional assumptions for it. sigma squared over n. Or an estimate would be s squared over n. Then when you get into the project number 1, I had to actually give you an estimate for that variance of s squared. I guess you could have used what was given in Cassell and Berger, if you remember. I think this was problem 3A of project number 1. But at the end, when we actually calculated this z and z star to calculate a studentized interval, I actually gave you what the asymptotic variance was, so that you had something to put in here. Well, what this whole section talks about is another way to come up with this variance. It's really not too bad in the end. It's kind of interesting how it comes about too. And then we're going to look at actually two ways to approximate it, and then we'll also talk about how the double bootstrap can do some of this as well. Okay. So last time we talked a little bit about Taylor series expansion. And Taylor series expansion is used to approximate a particular function. In essence, what we're going to do here is it's like a Taylor series expansion, but now for a statistical function. So what I'm interested in is approximating T of f hat, in other words, T. I'm going to approximate it with something that's simpler to work with. So this is kind of like in a Taylor series expansion, what we would call, let's say, f of x. So f of x in a Taylor series expansion is approximately equal to, let's say, f of a, if I'm expanding about a, it's a number of a. Well, when we're working with statistical functions, how about we expand about T of x? So notice you're working with an actual distribution instead. So that's how it's different from a regular Taylor series expansion. So T of f hat is approximately T of f plus, and then what we often refer to as the first order part of this expansion, x minus a times the first derivative of f of x evaluated at a. Now, what plays the role of this first order part of our expansion here is this guy. Okay. We're going to take the integral of what's called the influence function. And I'll explain on page 231 what the influence function is. You'll see it shortly, but just for now, just think that this is the influence function. It's the thing defined by L. And inside of L, it's dependent upon y. Notice the subscript t there. That's to say it's the influence function of t. And also something that's inside this influence function is dependent upon knowing the actual distribution f. And we're going to integrate with respect to f hat. Since we're integrating with respect to f hat, of course, and this is the EDF, notice what happens. Essentially what we're doing is we're summing, and we have a 1 over n out there instead. Okay? For now, you can think of this influence function as I put here, a measure the rate of change of T of f at some point y. So rate of change, that often deals with derivatives. In fact, derivatives are going to come up here shortly. Now what we can do is we can rewrite this expression here by taking this T of f and moving it over to the left side. So now we have T of f hat minus T of f, or equivalently T minus theta, is equal to, or is approximated by 1 over n times the sum of influence function evaluated now at y sub j, given we're working with f. Okay. Now to explain where we're going to go with this then, let's again talk about the central limit theorem. So we know that 1 over n times the sum I equal 1 to n of x of I, we learned this in 82, is approximated by a normal mu sigma squared divided by n. Where does this mu come from? It's the expected value of x of I. Where does the sigma squared come from? It's the variance of x of I. Equivalently, we could write this too as 1 over n times the sum of the xi's minus mu is approximated by normal 0 sigma squared divided by n. And I guess if we want you to write it like this, square root of n x bar minus mu converges the distribution to a normal random variable of mean 0 and sigma squared. Okay. Now, the central limit theorem is a very powerful tool because what you may not really have paid attention to in the past, unless you've had an asymptotics course, is the fact that you can put other stuff in there other than x. The key, maybe I could use x squared. So if I have x squared there instead, then this mu becomes expected value of x squared, and this is the variance of x squared. I could work with the log of x if I wanted to. The key is that you're adding up a bunch of random variables and dividing by the total number of random variables you have. Okay, that's the key aspect. So now, what I gave you in the notes is that we have this t minus theta that's approximately 1 over n times the sum of I equal 1 to n of this influence function. Okay, this influence function is going to contain some random variables. So what I can do is simply apply the central limit theorem to get the distribution of this average of the influence functions, which then gives me the distribution of t minus theta. This is done all the time in an asymptotic setting. Work with something that's a little bit easier to work with, and come back to what was a little bit more difficult to work with, t minus theta. So what that means then is, let me go back to my notes, is that this t minus theta is approximately a normal random variable with a mean of 0. Well, how do I know that? Well, I know that from, one can show that this expected value of the L, or just call it L, is 0. And this is given on, you can see it for the book. It's the equation number, equation number. Second here. It's equation 233, 2.33. You can see why the mean is equal to 0. It's just how we're doing approximation. And so then we need then this variance. Well, the variance is just simply 1 over n of the integral of the influence function squared d of f1. Well, where does that come from? Well, if I have a variance of a random variable, that's equal to the expected value squared of the random variable minus the expected value of the random variable, that quantity squared. Well, in this case, I have 0, so that's why I'm looking at that. Move over in, just from there. Okay, so that's my variance. So now I have a variance for t minus theta. Okay. Well, first of all, let's talk about this influence function. This is what it looks like. The stuff on the left-hand side here is the first way that the book writes it. Just kind of deals with the basic definition, what a derivative is. But we're going to also let the limit of this epsilon thing go to 0. So in other words, let's take the partial derivative of this statistical function. Don't worry about the stuff in here right now. Take the partial derivative of the statistical functional with respect to this thing epsilon and evaluate the derivative at epsilon equals 0. Let's talk about the stuff that's inside. Normally, we're we're used to seeing this, T of F. But I could put other distributions in there if I wanted to. So what we're going to do is actually put this, what you could say is a mixture distribution, because it involves two CDFs. It involves your regular CDF, F, but then this other CDF, H, which is, in the end, just a Heaviside function. It takes a jump from 0 to 1 at y. In other words, talk about the Heaviside function before. Here's 0, here's 1, here's my CDF, it's called H. And then once you're going on the x-axis, once you hit a point y, what happens is the following. Let me get a different color up. So you're coming along, let me make a figure. Imagine you're coming along here, and then when you hit that y, boom, you go up, and now you're at 1. So in other words, all the mass is at this point y. So either you're y or you're not. Very simple distribution. Very simple. Not very fun, but it works out well here. So what we're doing then is taking this mixture of F with this thing H. And look, if epsilon was equal to 0, we get just F back. But we're going to let, normally you think of epsilon as some small number greater than 0. Well, think about what happens then if I have a very, very small epsilon here. What this does, it changes your distribution a little bit. And one way to think about this, I thought that was a good way to think about it. This, in Layman's 1999 book, they just think it this way. Think about this as you're contaminating the distribution by this other point, this point y. And what we're going to do is look at basically the rate of change of my statistical functional if I contaminate my distribution by this y. So this is going to be a function of y. This is what this is trying to represent. We'll look at an example shortly of how you actually now calculate basically this stuff right here. So obviously you need to calculate T evaluated at this new distribution before you can get it straight. It's actually not too difficult. We'll look at it shortly. So again, we want to see what happens as epsilon goes to 0. So in essence, you can evaluate this function then at epsilon equals 0. This is your what's called influence function of a statistic T. So again, we're looking at the rate of change of the statistic. So this is this bullet here. Rate of change of a statistic when one value basically in the sample changes, let's say. So for example, what happens to the sample mean when a very, very large value is inserted? Well, of course, the sample mean is going to be greatly affected by it. What happens to the sample median? Well, it's going to be affected some, but eventually it's not going to be affected anymore at all. And this influence function gives us a mathematical way to display that. Oh, let's see here. So page 32, I give you just some more additional information to help you understand it. Even Cassell and Berger talks about the influence function. But this is where we really want to use this influence function. And again, we want to use it to come up with a variance. First of all, though, we need to talk about what's called the empirical influence function. So this influence function I define is dependent upon f. Well, you're never going to really know f. You're totally non-parametric setting, so how about we replace it with f hat? So when I replace it by f hat, then we call this the empirical influence function. And it's denoted in our book by L of y. Now when I actually write it out, because if I were to, I try to represent it just the way the book does with this little italicized L. What I will do when I write it out, I will actually use like a little script L, just to help differentiate it. Otherwise, it might look like a 1. Also, if instead of just having y there, if I instead write this as L of y sub j, let's say one particular observation in my sample, this has a particular name too. It's called the empirical influence value, basically for y sub j. With this as background then, non-parametric delta method variance estimates, which our book will refer to as V sub L. The L is emphasized that we're basically making a linear approximation, is equal to maybe I'll just back up a second here. We do a little split screen to see where this is coming from. So this is on bottom page 30, the bottom page 32. So based upon the central limit theorem, we know what this particular variance is approximately. Problem is we have an f there. So what we're going to do is replace it with an f hat. And in the end, it just ends up being this. 1 over n squared times the sum j equal 1 to n of these empirical influence values squared. Okay. So, throwing a lot of stuff at you. Why don't we take a look at an example? Oh, I'm sorry, this here?
Yeah.
This is just, the book uses a lot of notation to mean the same thing. This Lyj squared is also known as an empirical influence value. The book will then use a script, or I use a script. They're the same exact thing. I guess before class I wrote that in there. I failed to say it. Okay, so this is example 217 in the book. We're just simply going to work with an average. And I think this will go a long ways in explaining what we're doing. So let's let our statistical function T of f be mu. So let's say integral y df of y. The plug-in estimate that we learned at the very beginning of chapter 2 then would be T of f hat or y bar. Okay. Well, what happens when we change what goes inside the statistical function? So that now I have this mixture distribution in there. Well, simply, what happens is this. You take this integral of y df of y, multiplied by 1 minus epsilon. Okay. Plus, now, this extra part, the integral of y dh of y, multiplied by epsilon. So essentially what we're doing is you're putting the 1 minus epsilon of f in for f. That 1 minus epsilon is just a constant, so it comes out, the integral. Same thing happens with the epsilon. So, well, what is the integral of y df of y? It's mu. 1 minus epsilon times mu. Well, what's the integral of y dh of y? It's y. And I ask you, why? Because all the mass is on 1. So essentially what we're doing here is this. The sum over all possible values of y, corresponding to this distribution of y times the probability that a random variable y is equal to y. That probability is, well, there's only one possible value of y for this distribution, so all the mass is on that. So this probability is 1, and that's where we get this. So that's the influence function. I'm sorry, that's our statistical function evaluated this mixture distribution. So you can kind of get an idea then of what's happening here. Normally, we would have mu for T of f. But now it changes a little bit depending upon whatever this little point y would be. And obviously what epsilon would be. Well, what's this rate of change then? That's where the derivative comes in. This is where the influence function, that's what the influence function is. So now I take the derivative with respect to epsilon, and wherever I see an epsilon after I take the derivative, I put in a 0. So, obviously the derivative of 1 minus epsilon times quantity mu would be negative mu. Derivative of epsilon times y is epsilon. So I'm left with this. All the epsilons for this very, very simple function disappear. So my influence function is 1 minus mu. What does that mean then? Now I'm going to briefly talk about how this influence function is used in a robust statistics setting. So here's my influence function plot. So we have L on the y-axis, my influence function, and then possible values of y on the x-axis. And notice I purposely put in there one particular line for mu. And L of y, f is equal to y minus mu. So we can see that if y was mu, influence is 0. But as y is increasing, look what's happening. The influence of that y on the mean grows and grows and grows and grows. So, for example, in a very simplistic setting, even though this is a reference to a sample here, suppose I have this. I have a data set that has 2, 3, and y in it, where y is greater than 3. As y is increasing, what's the influence of it on the mean? It becomes bigger, bigger, and bigger, and bigger. And this influence function is represented in a mathematical context. Now, alternatively, what one could do is think of, well, I should say alternatively, in a similar manner, one could look at the influence function for the median. It ends up being this, and the book talks about it in terms of quantiles. I'm just going to, in terms of any quantile, I'm just going to represent in terms of the median. And this is a result from the book. I can give you a derivation if you wanted to. And this is what the influence function ends up being. 0.5 divided by your, if you happen to know the underlying density, f of m, so the density evaluated at the median, if y was greater than m. Otherwise, the influence function is negative 0.5 divided by f of m if y is less than or equal to m. So if you were to graph it, this is on page 35, this is what you get. Again, go back to my example of if I had a very small data set where values 2, 3, and y in it, where y is greater than 3. Draw. Fine. As y is increasing, what's going to happen to the median? Nothing. Notice this. This no longer, comparison to the one we were just talking about, the mean, no longer increases without bound. So this is a mathematical representation of the robustness of the median. Okay. Back to what we're going to be using the influence function for. Well, what's the empirical influence function? Well, the empirical influence function says, now instead of working with Ly of f, which is y minus mu, now the empirical influence function will work with Ly f hat. So mu, we know, will be the integral y df of y. Now we're going to say integral y df hat. So that mu becomes simply a y bar. So this is my empirical influence function. Now if I want to look at this function with respect to actual values in my data set, let's say y1, y2 down up to yn, or let's say y sub j in general, then I have my empirical influence values. L of yj, or I can use, let's say, script L sub j. And why do we want these? To get the nonparametric delta method estimate of the variance. So V sub L is simply 1 over n squared times the sum of all your empirical influence values squared. So I put in yj minus y bar, do a little algebra, and I get this. So notice, this is just simply, you could say, the the biased version of the estimate of variance for a sample mean. That's all. Of course, the same goes to infinity. It's going to get to about the same spot as the, it's going to get to the same spot as the regular old unbiased version. Where?
Remember the unbiased estimated variance was.
No, that's right. Well, sorry, I didn't say what S squared was. It's this. Okay. So let's apply this now to a data set. So this is the air conditioning data once again. As I've noticed that sometimes students have problems remembering what's the influence function, the empirical influence function, the empirical influence values, and all that stuff. I've actually summarized this in a table. Remember, with the AC data, we're interested in the mean, so that's why this is a nice second example. And so what I could do is just simply go to my data set, put in the yj's, calculate y bar, you got your estimate of the variance. Let's look at a way that R can automatically calculate the empirical influence values for us. This will save us some time. Okay. So this is in the program emp.inf.r. So remember, we just have 12 data values with the air conditioning data. The function that we're going to use is the emp or emp.inf function that will automatically calculate the empirical influence values for us. As you might expect, there's an argument called data. You pass in your vector data. There's an argument called statistic, where you write a function that calculates your statistic. But this function has to be written in a different way than what we've seen before. So you might be thinking, well, why don't you just put in your usual calc.t function? That doesn't quite work here. Instead, I have to write the function in this form. So calc.tw, W is going to stand for weights. Function, data. I'm going to find some weights by default. These weights, it's going to be a vector, and by default it's just going to be 1 over n, 1 over n, 1 over n, corresponding to the every data value that you have. Then I say D gets my data, and then I have to write then my statistic in this form. The sum of all my data values, where notice each of them are weighted by what will be by default, 1 over n. So in essence, this is kind of like writing out the integral of y df hat. So that's what you need to write your integral like. I'm sorry, write your statistic like. The reason being is this. This Empi function is going to actually change the weights to help take a numerical derivative. We'll take a look at the actual code for Empi if you want to see how this is done. I'm not going to ask you a direct question on the test. But that's essentially what's happening. This S-type argument stands for I'm working with weights. So statistic type, S-type, it's a function that's written in terms of weights. Just to verify to begin with that indeed that this function is going to give me the same result as if I didn't write it in terms of weights. How about if I just run it with my data, I get 108.08. I did the mean of y, 108.08. Okay. So, I'm going to now use the Empi and IF, put the results in L dot J. There's my empirical influence values. So we're taking numerical derivatives. We derive them to be y sub j minus y bar. So let's check to see if indeed I get the same thing, and yes I do. So you can see that this function that's been written can be quite helpful. Saves you some derivations. Well, let's actually now calculate the variance that I have now that I have these empirical influence function values. What I could do is just simply use the sum function L dot J squared divided by n squared, or there's a function R called, this is in the boot function. I should say this is all in the boot package. var dot this Empi and INF function, and also this new function var dot linear. And oops, what happened? My hand's wrong. There we go. Get the same thing. Okay. Any questions so far? Let's look at a little bit more complicated statistical function. This is on page 37 now. Let's work with the variance. So, sigma squared written in terms of a statistical function, T of f. Of course, it's the integral y minus b squared df of y. You can multiply some stuff out inside that integral so that you write out then the integral like this. The integral of y squared df of y minus the integral of y df of y that can be squared. The reason why I do that is because it's easier to work with it in this form than in this form when you're working with an influence, when you're trying to find the influence function. Please note that there are some small typos. I hope you can see that. There's these plus signs. They should be minus signs. Here's one. I should try that. And here's one. Looks better, or you can see the blue a lot better on my screen. I changed the notes maybe very early in the semester, so if you, that's okay. I think it was the first week of school I changed. Okay. So, we've already looked at this part right here, how to write it in terms of this mixture distribution. And we just basically apply the same concept then for the second moment as well. We get some simplifications. Just have expected value of y squared there times 1 minus epsilon plus epsilon times y squared. And then we've got the stuff that's in a square over here. Makes it a little bit more difficult to work with. So let's do the influence function. Let's take the derivative with respect to epsilon, evaluated at epsilon equal to 0. I'm just going to remove all these red circles here because it's distracting. So, take the derivative as you would normally. All of you know how to take derivatives by now. The key thing is that notice when we're working with this quantity squared, you just apply the chain rule. So this 2 comes out front. You got the stuff that's still inside, and then you take the derivative of the stuff that's that was originally inside. Note that epsilon doesn't disappear after we take the derivative, so we're going to plug in epsilon equal to 0. So look what happens here. When epsilon is equal to 0, we end up just getting a mu that pops out. Go through some more math, and we get this here. Y minus mu squared, that quantity, or y minus mu squared minus sigma squared. So what are the empirical influence function values then? Empirical influence function itself. Well, now we use the plug-in estimates. In other words, mu will be just the integral of y df hat. Sigma squared will be the integral of y minus mu squared df hat. In other words, it's going to be the usual bias estimate of the variance. So let's see our empirical influence function. The empirical influence function's values, we'll just take that y that's all by itself, put a yj there instead. And so again, that's your LJ, your empirical influence values, so that then the non-parametric delta method estimate of the variance then is just 1 over n squared times the sum of these LJ squared. Okay. Now, the reason why I did this particular example is because this semester with our projects I chose to work with sigma squared. And remember from the project number 1, we can actually find the variance of S squared itself. Obviously, there's an n minus 1 in it, but again, asymptotically, it's not going to matter. Instead of having just an n in the denominator. So the variance of S squared can actually be shown by number 5.8 of Castellan-Berger to be this quantity there. A plug-in estimate, you could say, of it just simply takes this fourth central moment and take 1 over n times the sum of yj minus y bar to the fourth. Do a similar thing for sigma squared itself. And so that's an estimate of the variance of S squared. Now I might be thinking, geez, that looks a lot different than what's up here with the non-parametric delta method. No, actually it's not that much different. What you can do, I'll let you go through the details on your own, is actually multiply some stuff out, do some algebra, and you can show the non-parametric delta method estimate of the variance is this right here. And again, look how similar that is to, you could say, an exact estimate. Asymptotically very fluent. And the thing that's different is this right here. Of course, that goes to 1. Well, how does this all compare then to this asymptotic variance that I gave you for project number 3? So this is that, project number 1, problem number 3. This is towards the bottom. And this is what you end up using for when you're doing the studentized interval. Well, again, one can show square root of n times s squared minus sigma squared. It converges in distribution to normal 0, fourth central moment, minus sigma to the fourth. Well, what will be the corresponding estimate? Well, I'll just put the hats on there, and you remember this ends up being very similar, actually the same. So that's nice. Now, what I would like you to do on your own is to make sure, actually I think this might be part of project number 2. That's essentially part of project number 2. So make sure that you can program in these empirical influence function values into R. And then you can also use the Empi function to get the same exact values. So, since I mentioned the project, why don't you take out the project and we'll discuss it. At least part of it. Unfortunately, I closed out my file. Okay, let's actually look at problem number 2 first. So problem number 2 involves the fourth central moment, mu4. I was actually going to make this all about kurtosis, which involves the fourth central moment. I decided just to make it easier, just do the fourth central moment itself. So this is the fourth central moment. What I want you to do is give me the plug-in estimate. You should know what that is already. Next, derive the influence function for mu4. I recommend that you multiply out the y minus mu to the 4th power to do this. What's an easy way to get the necessary terms? What's that? Binomial theorem. We can think of it in terms of Pascal's triangle. This derivation took me, at least typed, 1.5 pages. Just to let you know. But then again, I use a lot of spaces and I'm trying to make it look nice. I hope you make yours look nice too. But that's how long it took. Next, well, what are the empirical influence values? That shouldn't be too hard. The key thing is getting the influence function. Get the non-parametric delta method estimate of the variance for t, and then use the Empi function in the data set that's actually used in 1 to verify your derivations for the problem are correct. So you have a way to know that you got the correct answer.
I'm assuming in C and D, where you're finding the influence values, and to use the data set there, or?
Well, you're going to write it in terms of y such.
Okay. Okay.
But the key thing is here, you will know when you get the right answer. Unless you messed up both in the derivation and in the implementation of Empi. I hope that doesn't happen. Then problem number 1. It's a continuation of problem number 3 of project number 1. So you're using the same data set. What I want you to do is calculate the empirical influence value and the non-parametric delta method estimate of the variance of t using the formulas that we just talked about. So you obviously don't need to derive them, but I want you to make sure that you can program them into R and you do the calculation. But then, using the Empi function, find the empirical influence values. Again, you should know when you got it right, because you know what the correct value is based on what the notes are. As long as you can substitute the actual numerical values of the y's and j's incorrectly, you should get the same values. The rest of this I'm going to hold off on discussing until we do some more stuff. But this will at least get you started on it. I want to at least get that far today in class. Are there any questions? Okay. Yeah.
How did we know that sigma tilde had to be the biased estimator?
It's because you're using the plug-in estimate. So if I plug in f hat and I'm taking that integral that you would have for T of F. That's why it's the bias estimate. So it goes back to section 2.1. Now, often you're given a situation where you can write your statistical function as a function of multiple statistical functions. So let's let T of F be then a function of, let's say, T1 of F, T2 of F, all the way down to Tm of F. So m different other statistical functions. We'll call this function A of these functions. So for example, where this comes into play is with respect to the coefficient of variation. There's a small change I want you to make in the notes because it corresponds to then how I do this example. So the blue part there is what I want you to have, not the stuff that's right here. So suppose that T1 of F is sigma squared, T2 of F is mu. Then we could write the T of F, the coefficient of variation, as T1 of F square rooted divided by T2 of F. And we can say in general this is the function A of T1 and T2. Now, in order to find then the influence function, it's actually not too difficult if you know the influence function for T1 and T2. Simply, it's this, where you're just going to sum over all the statistical functions that you have, let's say m of them, take the derivative of A with respect to T sub I, and then multiply that by the corresponding influence function of T sub I. That's it. Make your calculations a lot easier. So for example, here's the coefficient of, let's do this for the coefficient of variation. There's two statistical functionals in it. So I'm going to take the derivative with respect to T1, then multiply by the influence function for T1. Take the derivative with respect to T2, multiply by the influence function T2. Okay. Now we had just derived the influence functions for both sigma squared and also for mu. So all we need are basically these derivatives. That's one reason why I changed my notes from what was actually on the web the first week of class, because this would be a little bit easier. Before I had everything written in terms of the standard deviation. Okay, so I need to find then the derivative of this. Why am I writing it? I don't know why I was writing on an angle. Okay. Just to make things easy, because it can get a little bit confusing, how about if I let b be equal to sigma squared? So in other words, I need the derivative with respect to b of b to the 1/2 divided by mu. Obviously, the mu doesn't play a role. So if I take d to db, I get 1 over mu times 1/2 times b raised to the negative 1/2 power. If I write this now in terms of sigma squared, then this is going to be 1 over 2 mu times sigma squared raised to the negative 1/2 power. In other words, 1 over sigma. And that's what we got right here. Next, to get the derivative with respect to t2, that just means take the derivative with respect to mu of sigma divided by mu. So what is that? Just negative sigma over mu squared. Multiply some stuff out, and here is my influence function. Now, what you should do on your own, make sure you can do this, is to program into R code such that you can calculate then the empirical influence values. Obviously, you need to know what the empirical influence function is, and then also use that to obtain a non-parametric delta estimate of the variance. Make sure you'll know when your answers are right if they match up with Empi and IF and bar.linear. Okay. Well, there are other ways to work with or to get empirical influence values. When I say to get, I'm actually saying to estimate them. That can be actually a little bit easier. We're going to talk about two ways. One, using the jackknife, and another one using basically a regression model. So the jackknife, I would expect all of you have seen it somewhere before, even though it might not have been called the jackknife to you. Most of you have probably taken, for example, Stat 873 multivariate analysis. When you do discriminant analysis and you use the cross-validation method to estimate basically to estimate which class you're going to, let's say, predict a particular observation to fall within. And then also that helps you get close to being unbiased estimates of error rates in terms of classification. What do you do in that kind of setting to do this thing called cross-validation? Well, you remove one observation from your data set, you do all your discriminant analysis calculations, and then based upon that, you try to classify that particular observation that you left out of the data set. You do that for one observation, and then you go to, let's say, the next observation, do exactly the same thing. That's a version of the jackknife. If you want to, I'm going to give you a brief explanation of the jackknife, how we're going to use it. A little bit longer discussion is in Efron Tibshirani's Bootstrap book. Actually, even the jackknife can be thought of as a special case of the Bootstrap. I think it was invented in, if I remember right, the early 70s. It might have been the 60s. Tukey came up with it, and in fact named it. So you can think. So Tukey named the Bootstrap. He also named the jackknife. So he liked interesting names. So the jackknife can be used to estimate L sub j. We're going to call the estimate L jack of j. And simply put, this is the estimate. Sample size minus 1 times your original observed statistic minus that observed statistic but without the jth observation. So pay special note where the j's are. The j here and the j here. So if you have a sample size of 10, t sub negative 1 would be the statistic calculated for observations 2 through 10. So this is L jack. And essentially what it is, this L jack is going to serve as an estimate for L sub j, where in essence, and this is actually a problem, a homework problem that's in the book. I've given this as part of a project, and this time I just didn't do it. it essentially serves as approximation to what the influence function would give you if you, instead of saying epsilon equals 0, say epsilon equal to negative 1 over n minus 1. Take a look at this problem if you are interested to know more about that. So then, to estimate then a variance, so before we had V sub L, now we're going to have something we call VJAC. And VJAC is 1 over n squared times the sum of these jackknife estimated empirical influence function values squared. Or in other words, n minus 1 squared over n squared times the sum j over 1 n t minus t sum minus j that quantity squared. So that's an estimate of the variance. Jackknives are used a lot in statistics to estimate variances. Our book expresses this formula in a different way. It's actually a slightly different formula. So you can see, let me have both on the same screen at the same time. So you can see we still have this squared L jack. You have what kind of looks like 1 over n squared there. But they also have a term with respect to the bias. And they estimate the bias, they get a jackknife estimated bias, don't worry about where this comes from. Negative 1 over n times the sum of the L jacks. Now, this is the only time that I've ever seen basically the bias represented in a variance estimate that comes about for the jackknife. Yeah, you know, you could have a bias statistic that you're talking about, but even so, the bias is probably not going to be that great, because why would you choose that statistic in the first place? So I'm not going to worry about the bias here. And what's interesting too is that the corresponding functions that they program into, I guess in the day was S plus, and now that are in R, when we actually find the variance, this isn't accounted for anyway. So it's kind of interesting that they even would put that there.
So they talk about it in the book, but they didn't implement it.
Yeah. Well, what about then this over here? Why don't we have 1 over n squared? I know when I first saw this, I was curious about it. I mean, it's a minor thing in the end. But this is what I came up with in my investigation of where this comes from. As Efron and Tipshirani say in their book, it is somewhat an arbitrary convention. Our authors say, well, in example 2.21, the denominator n minus 1 in the formula for VJAC was chosen to ensure that this happens. In other words, you get an unbiased estimate where you're just talking about the mean itself. So in order to get an unbiased estimate of the mean, where your mean is your statistic of interest, that's where this n minus 1 comes from instead of using n. But obviously you could use this jackknife estimate of the variance for other statistics than just a mean. But because it works well with the mean, that's why it's in there. It's not worth it. Just do 1 over n squared. Okay? So this is the formula I'm going to use to do a jackknife estimate of the variance. I want you to use this formula in our class. If you get outside of this class, you want to use a different formula, go right ahead. I won't change your grade in this class. We need to talk some more about this formula. Other books, not necessarily, I'm not talking about Bootstrap books, but other books where a jackknife estimate of the variance is given. I guess Efron and Tipshirani talk about this too. They'll use this formula, and they'll also use this formula. In the end, they are all just about the same. If you want to know more where it comes about, take a look at references. I guess I'll give you a reference at least for one of them there. But the one that you will see most often applied is this one. I actually, I think it's now 4 or 5 years ago, I wrote a paper that was published eventually in the Canadian Journal of Statistics. And I actually ended up using, for the derivations I was doing, deriving a new statistical method, I actually ended up using this formula. And a referee said, "Where does that come from? Why did you use this formula?" And so I had to explain to him, see such and such reference. This is the often referred to as a plug-in estimate. And ref was okay with it, so everything was great, and the paper was published. So I just want to at least mention that this is often a more used formula out there. Okay. So let's talk about then working with the average. This is a real nice application that shows what the jackknife does. So what is actually T sub negative j when we're working with the average? Well, it's a sum of all your y sub i's except for, let's say, when I is equal to j. And notice what I have to divide by, n minus 1, not n, because I have n minus 1 data values. So you can actually rewrite the numerator so that you do have this full sum, the sum over all your y's, and then just subtract off y sub j. And you can then rewrite it a little bit like this, ny bar minus y sub j over n minus 1. So you can write it like this. And you can see the effect that working with the jackknife has on your statistic when you remove that one particular observation. Obviously, as n gets big, the effect is less and less and less. Well, what's L jack then? Well, you can take n minus 1 times t minus t sub negative j. So that's what I did. Do a little bit of algebra. And look what we are left with. Y sub j minus y bar. Hopefully that looks familiar, because that was alpha sub j. So that's nice. Remember that LJAC is supposed to be an approximation to LJ, and in this example we did exactly the same thing. So then what's VJAC then? Of course, obviously the same thing we had with the empirical influence values. So in the project, I asked you, when you're working with the sample variance, to basically do the jackknife. So get the LJACs, get the estimate of the variance. So then the next way that we can estimate the variance then is if we approximate the empirical influence values via regression. This is a little bit, it can be a little bit more difficult thing for students to understand, and I like to actually talk about all my write-up on it all at once, and I don't think I can do this in 5 minutes because there's going to be extra stuff I'm going to write out. So why don't we just stop here? Are there any questions?
On the project where you say to find the jackknife estimates,
yes.
There in 1B it says use the Empi and F function to do that?
Yes.
Do you have an example?
Yeah, that's actually coming up.
Okay.
Yeah, that's coming up on page 49 and 50. So if you want to get a head start,
okay,
you're welcome to read ahead. 49 and 50 will help you with the jackknife estimates and the regression-based estimates in Part B. Okay, that's it for today.